where we left off, and we'll start with this. So now we're talking about rheology, which is a fancy word talking about how fluids respond to applied stresses. So you can think of that as pumping or a fan. So if you apply a stress, if you try to push a fluid, how does it respond? And you remember drag was looking at the shear stresses of the fluid on a surface, say, like a flat plate. And that shear stress times the area was a drag. Well, now we're looking at what's going on between molecules in the fluid. And in most of your experience, you're used to Newtonian fluids, in which there's a linear relationship between resistance to flow, the viscosity, and the speed. So on the x-axis here is shear rate in inverse seconds, and that's like the pumping speed. And here you have the shear stress on the y-axis. And so Newtonian is like water. It's what you're used to. It's also air and oil. The three fluids I think are most important in our world. And then there's blood. And blood is actually pretty Newtonian, but it's like toothpaste. It's a Bingham plastic. So Bingham plastics are fluids that don't move until you get up to this higher shear stress. So you squeeze on the tube with toothpaste, and then it starts to flow in sort of the conventional way. And dilatant. Now I'd like to go back to these. I'll look at these more dilatant and pseudoplastic. You can see they vary. One gets thicker as it goes faster, one gets thinner as it goes faster. We'll explore that. But before we did that, I want to look at viscosity. And there's a lot of terms here, and I wanted to elaborate it on a little bit. In our world, we're going to kind of stick with what's called dynamic viscosity or absolute viscosity. There's another called kinematic viscosity, which is related to buoyancy. And I just wanted to give you the term so you saw it. But dynamic viscosity is really what you're talking about when you're talking about resistance to flow. It's what you're used to. Squeezing on the toothpaste, okay, the viscosity of your toothpaste. That's what that's all about. And kinematic is where you divide it by the density. So it's when you, and it sort of makes sense because air has a certain viscosity, but it also has a certain density. So it makes it, if you pour water into a bucket full of air, the density is more important than the viscosity. And that's where kinematic viscosity comes in play, looking at the relationships under gravity. So let's just focus on dynamic viscosity. And in fact, I put the kinematic viscosity chart, I put it kind of small just to put it there. And really, one of the things I'd say with teaching, especially what we're doing here, is you can really get overwhelmed by terms, by minutia, and also by math. So I'm trying not to do that. So I'm basically saying forget kinematic viscosity. And say for most cases, you won't have to worry about it. So here's an example of ranges of viscosity. So this all makes sense to you. Ketchup and such, and fondue, toothpaste are at the far end. This is in centipoise, an SI unit, and gases are at the far end. Okay. And so things get thicker. Now here this is looking at air and water. So we're in air and water's viscosity varies a little bit with temperature. And you may know motor oil varies a lot. And other fluids too, honey and molasses, these kind of things, they vary a lot with temperature. And this is just a profile of absolute or dynamic viscosity versus temperature. But more importantly, I wanted to show you the difference between these. So these are logarithmic relationship on the y-axis. So water is a lot more viscous than air. No surprise there at all, right? So yeah, it's easier to go through air than it is through water. So when you push your way through air, the intermolecular surface forces of the air are very weak. They get out of your way. In water, that's not the case. Water does not want to let other water molecules go, and that resistance to shearing is viscosity. So again, you're familiar with this, but I just wanted to show it to you graphically. And here's a lot more fluids, which we don't have to go over, but if you look at the motor oils, they change a lot with temperature. So you have temperature on the x-axis, viscosity on the y-axis, and you see you've got the gases way at the bottom here, methane, air, helium, the weight, they're very low. Then you have water and fuels down here, and then you have these oils way up here. So at low temperatures, like bunker oil, number 6 oil, it's tar. It does not move. It has to be heated to move. And anyway, again, just a graphic. I hope that sort of helps you just see that. This is based on your personal experience. These are just throwing numbers and sort of a busy chart add to that. And we talked about water before, and just to repeat it, it's the reason we like to use water wherever we can is it's got a lot of these benefits. It's Newtonian, meaning it's very predictable in the way it's hot. So when we look at non-Newtonian, you're going to see where things suddenly get weird and not unpredictable, but it's strange. They get more different. It's safe. It has that high specific heat that we talked about, meaning I don't have to raise the temperature very high to move a lot of energy with it. And then this high surface tension that we talked about before too, which keeps it from leaking, makes it easier to make joints with than other types of liquids. And semi-bad stuff, we call it design, but it does expand as it gets below 39 degrees Fahrenheit, 4 degrees Celsius. And that's why ice floats above water, which is vital for aquatic systems. So you get this ice layer on top of ponds, so it doesn't kill everything as it frees up from the bottom. So you think of things getting colder, shrinking. Well, that's true with water up to this point. Then it starts to expand a little bit. Boiling water is dangerous, and you can, if you pressurize the system, you can get well, steam can be any temperature, of course, but even water, even with high pressure systems, becomes really dangerous when it flashes to steam. I told you stories about how they used to. I don't know if it's apocryphal or not, but they used to detect. I don't think it was a good source. That's all it is. They would detect your steam leaks using a broom and cut off the bristles if it was encountered a leak. And then again, it thermally expands like most every other material, and it is polar. There's a strong polar component. That's why surface tension is so high. There's a plus and a minus. So it tends to be a solid that tends to be these things because of these strong polar forces. And it doesn't train gases. And gases are a problem with corrosion. They're a problem, well, not so much with cavitation, which is a different thing that I'm not talking about here. But training gases is an issue with corrosion. And also, if you have gases entrained in water, it can lower your specific heat at some point. All right, now we're going to look at non-Newtonian. And here we'll talk about blood first, which is like toothpaste, the way it behaves. And there's a little reading in the book about it, in the white book. And when we deal with non-Newtonian fluids that don't act like water, you're often talking about aggregates of a solid and liquid, which is called slurry. So a liquid and a solid is a slurry, a solid and a gas is a smoke, and a gas and a liquid is an aerosol. So you've heard all those terms. So these are practically slurries. And when you have particles of different sizes, they're called polymodal slurries. Poly with multiple, modal, different sizes. So you can pack a lot more solids, like into something if they have different sizes. So if you take a bunch of ball bearings and put them in a bucket, you can get a certain number of ball bearings. If you take ball bearings that are smaller, they're basically invisible. They fit between the nooks and crannies, the interstitial spaces of the big ball bearings. And you can keep doing that. And by doing that, you can pack a lot of solids into a liquid. And so liquids are carriers. The liquid around, which we're talking about plasma here in the case of blood, it's it lets the solids flow. And so blood is a good example to look at because things like quicksand and oobleck and all of this sort of stuff is largely like this. Now there's some non-Newtonian fluids that have these really long molecules, so there's different phenomena, but this is probably the most common. And one of the things that's unique with blood, a couple of things, is the cells are deformable themselves. And when you look at the video here, when you get a chance to go through the PowerPoint, you'll see blood flow in action. And what happens when blood is traveling quickly, the plasma, the supernatant liquid about the cells, flows faster, and the cells kind of cluster behind it. And so what happens then with and plasma is what initiates the clotting mechanism, and there's more description than in the book. The plasma kind of leads the charge, and the white and the red blood cells lag behind. But blood is unique in that it when it pumps slowly, it has high viscosity, like toothpaste. It doesn't want to pump, and at high speeds, it pumps smoothly or easily. So in your main arteries, you can push blood around very quickly, whereas as it gets into the capillaries, it's slowed down. It's flowing slowly. And you've got the deformation of the cell. It's actually squeezing. So all the biological requirements of moving through cell membrane walls and such are helped, aided by this slow movement of blood. So it flows slowly, or has high viscosity at low speeds, and low viscosity at high speeds, but it acts a lot like toothpaste. And so when you see the video, that will make more sense to you. And the reason I think this is, I got a little more. Okay. This is an example, so it's a big in plastic. And this is actually a little bit different than the other chart I showed you. I also threw in here the specific things. So water is 4.18. This is SI units in this case, but I don't care about that. Blood is 3.49, so it's a little bit lower. So, but it's still very high. So blood is a good way to move heat energy. It's not as good as water, but it's still very good because blood is largely water. Well, I don't know what percentage of plasma is water. Anyway. That's always a safe answer. Okay. And yeah, there's some videos you can watch. And okay, now we'll look at non-Newtonian. And with non-Newtonian, well, I guess what's interesting, I mentioned in the bike problem about the rheology of the air that you're pedaling through. And there's two factors there. One is when you say the word rheology, 99% of the people don't know what you're talking about. Okay? So it either gets you in the club or it makes you sound like yin-yang, I don't know what, but it's the right term. And it's sort of the first question you ask when you're dealing with fluids. You say, what are the rheological properties of this fluid? Because if they're non-Newtonian, that means it's a little more difficult to deal with. You've got to kind of predict these things. And I'll just give you like one example, semi-practical example. Well, I guess a lot of examples, but one is heavy oil. I talked about it before. So heavy oil is real thick, number 6 oil, which means you can put it in tanks. You don't have to worry about it leaking too much. You know, it's like tar; it doesn't want to leak. But it means that for you to move it, you've got to heat it. So you move it; it becomes a lower viscosity, and you move it slowly between tanks or whatever. But then when you go to burn it, you're running it through an atomizer, which is a really, really high shear rate, a high pump speed. It's going really fast. Well, it now behaves very differently than it did back when it was being pumped out of the tank. And if you don't know that, you won't know how to design for it. In other words, you're dealing basically with two types of, well, in the scenario I gave you, it was kind of 3 types of liquids. One was cold, one was hot, but then one was low velocity, this like transfer pump going from a tank to something else, and the other is high velocity, going from the atomizer. So in that way, you really have 2 different fluids act very differently. And so it's a reasonable question to ask, is the fluid you're dealing with act that way? And here we have dilatant, I have dilatant and pseudoplastic. We already talked about plastic, so I won't repeat that. But with dilatant, it means that the viscosity increases with the stress. And we think a quicksand is being an example. So something can be kind of liquidy. I've got a video on that. You can move through it, and then if you move quickly, it locks up on you. I don't have any silly putty here. I don't have it in any work either. I try to find it. But silly putty is a good example. You can stretch it with your hand, but if you roll it into a ball and bounce it, it will bounce. Because if you bounce it against the floor, the shear rate on the silly putty is really fast, and it goes sound. So silly putty goes from this kind of almost a liquid, an easy flowing plastic, to a solid by how fast you apply load to it. I have a video on oobleck too. This is a cornstarch water blend. You can walk on it because you're applying force quickly. So something goes from really liquidy to very solid-like. That's dilatant. The other is pseudoplastic, which is the opposite. Now I did have blood in there because blood is kind of complicated because it's a bingo plastic and it's a little pseudoplastic too. But let's hold off on it for a moment. So pseudoplastic, you may, I mean, one thing that most of us have dealt with is paints. So paint can be hard to mix at first, and then it kind of breaks free and it's easy. Molasses is certainly that way. Ketchup is too. So this is the opposite of dilatant. So something's very difficult to work with initially, and then it becomes easy. So those are really helpful terms. And this is that same chart showing you kind of how these things vary with shear rate. So again, shear rate is the same as pumping speed, and shear stress is the same as viscosity. Okay, and then I just want to give you these words. I don't. I'm not going to elaborate on this, but this thixotropic, which is actually a big one because it does apply to paint. So where the viscosity changes with time, and the synovial fluids and joints is one where you have the viscosity increases the longer the stress is applied, which is really unusual. I got some videos on that. But these are esoteric, so I don't want to mix them in. Now, actually, I'm doing really good time. Oh, this is great. So I can go over, let me go over just these three items, and then we'll see what questions you have about rheology. And I want to go over, this is a repeat, but I have some more graphics for you. So Weber number, Reynolds number, and Mach number, just with graphics. And then I'm kind of excited because we're really putting a big ribbon around everything. Actually, this in the next moments will really be done with the core of the class because we do want to go over Bernoulli and stuff. And then we'll deal with a little bit with combustion and some other things. But anyway, okay, Weber number, inertia over surface tension. We talked about it. I did find a little diagram that sort of helped. So this is how much things want to stick to each other, divided into how much velocity they have, inertia. And high Weber numbers can be small droplets, and low Weber numbers you don't really get pretty good stuff on the fluid. So I have to be honest, this isn't probably something we're going to deal with too much. Okay, but I think it's helpful. There's other dimensions parameters too, but it's a cool number. Okay, Mach number. I found this from NASA, so it has to be right. And you know this, but this is divided into the speed of the object. And it's a big issue. When you think of this, you think of, well, shock waves, I guess, but think of high velocity gases as being incompressible. So that's why you get shock waves. So Mach number is important for you in that way. And it can really happen at the tips of fans. I don't know if bicycles are fast enough to get Mach speeds, but you can get, these things actually happen, or getting compressibility effects can happen in things in the day-to-day world, where the Mach number gets big enough to have a compressibility factor. And what happens with the Mach number is, or the ideal gas law is modified with a Z factor, which is related to Mach number. So for the ideal gas law, pressure times volume equals nRT. Well, you add a Z term in there. That the relationships are all the same, but it's not linear like it once was. And with that, I got to put a plug in. You got to look at the simulators. I created a new link in Plato for the ideal gas law simulator and the flow simulator. And you've got to try them and experiment, and we can talk about it here in just a minute. Okay, Reynolds number, we talked about this. Reynolds number, like 10 years from now, Reynolds number, if you just think Reynolds number equals velocity, I'm happy with that. Okay, that's basically what it is. It's basically telling you velocity. But it's really cool because it lets you move between, you can do things with scaling and modeling, you can work with different fluids. It tells you that, you have this battle between inertial forces and viscous forces. So inertial forces, where things want to keep moving, and these viscous forces where things want to stick to each other. That's the battle. And like if you look at flow over a cylinder like we looked at, you get these retrograde motions behind the cylinder where the flow is actually backwards, and it tends to separate that boundary layer like we talked about before. But this is the equation, not a big deal. But I've got a really cool question for you here in just a moment. Actually, maybe this is a slash. Yeah. Okay. Yeah. That's okay. That works. That slide right there. So let me. Yeah. Let me. Why now? Maybe you remember this. when I asked you about if somebody said, I want a low Reynolds heat exchanger, I want to, why would somebody want a low Reynolds heat exchanger? Somebody want to offer an answer to that super geeky question? And this happened in Cayuga Lakes, all right, that lake source cooling. Well, you think about it, lake source cooling system I showed you. Those heat exchangers are advertised as low Reynolds heat exchangers. And any thoughts on why they would use that term? Yeah, okay. Wait. Oh, okay, that's from Zoom. 10 minutes. All right. Whoa, how did that happen? All right, low Reynolds heat exchangers. Well, why you would use those is low Reynolds is a fancy word for low velocity. Anyway, so the reason you want low velocity through a heat exchanger, the only reason you want it is to save money on pumping costs. That's the only reason you want it, right? Because you know that convective heat transfer is a function of velocity. So high velocity gives you high convective heat transfer. So, and you know about turbulent boundary layers. A turbulent boundary layer will give you higher thermal conductivity. So, in other words, if you were to design a heat exchanger, you want a high velocity heat exchanger. And here we're talking about water and water. And that means high velocity gives you higher convection coefficients, you get a turbulent boundary layer, et cetera, et cetera. But the downside is pumping costs. And that's real, it's important. They don't stop. You're always pumping fluids through heat exchangers. So a low Reynolds heat exchanger does two things. One, it just gets into the club. Instead of saying I want a low velocity heat exchanger, I want a low pumping cost heat exchanger, you say low Reynolds heat exchanger. It's the same thing, it just the language. But then what you have to do is you want to, so this means the fluid is flowing slower. So what you want to do is trip it into a turbulent boundary layer quickly with roughness, like the bowling ball problem we talked about. Turbulators, they use chevron shapes, you use different things to cause things to go to a turbulent boundary layer at a low Reynolds number. So that's super geeky, but that's there's a lot in that statement. Low Reynolds number just means low velocity, low pumping speed, but you still want turbulent boundary layers. Okay, well, I'm excited. There's the fluid sim. I had a little thing on the PowerPoint for blood platelet formation and some other things I'm not going to really talk about. But these simulators I have one here in PowerPoint. I also have them as a separate Zoom link. You really got to explore it. There's actually I can't do it on this because whenever I do a video, just everything slows down. But there's actually one feature in there where you can get a sensor and you can locate the sensor at different places. And you can look at it will give you the X velocity, the Y velocity, which I don't care about, and it'll give you the density. And you can move that sensor around. And it's got a battery of defined shapes. It's got airfoils and cylinders. You can draw your own shapes. So you got to try it because I mean, I've been talking at you, but you got to try these kind of things. And I don't know exactly how to, I mean, just mess with it. You're not going to break anything. You got to explore like I said, there's these data points. Just explore all the different options in this one, and it will help you because just hearing words isn't enough. And then beyond that, SolidWorks, many of you know SolidWorks has a package. I sent a link to you on how to use a flow simulator in SolidWorks. And I mean, you got to be careful of that because if you just sit there and look at dots and go through things, you have no idea what's going on. That's dangerous.